Imagine standing at the edge of everything you know, peering into an abyss so profound, so absolute, that not even light itself can escape its grip. Imagine a place where the laws of physics as we understand them simply stop working, where time bends, stretches, and ultimately freezes, where matter is crushed into an infinitely small point of unimaginable density. This is not science fiction. This is not a story conjured by the imagination of a novelist. This is real. This exists in our universe right now, scattered across the cosmos in numbers that dwarf every grain of sand on every beach on Earth. We are talking about black holes, and today, we are going on a journey deep into one of the most extraordinary, terrifying, and beautiful phenomena the universe has ever produced. Before we can truly appreciate just how mind-bending black holes are, we need to understand what they actually are at the most fundamental level. A black hole is a region in space where gravity has become so overwhelmingly powerful that nothing, absolutely nothing, can escape from it once it crosses a certain boundary. That boundary has a name. It is called the event horizon. Think of the event horizon not as a physical surface, not as a wall or a barrier you could touch, but as a point of no return. It is the invisible line in space where the escape velocity, meaning the speed you would need to travel to break free from gravity's pull, exceeds the speed of light. And since nothing in the known universe can travel faster than light, anything that crosses the event horizon is gone. Forever. Trapped inside the black hole for eternity. Now, gravity is something we experience every single day of our lives. It is what keeps your feet on the ground, what holds the moon in orbit around Earth, and what keeps our entire planet circling the sun. But the gravity around a black hole operates on a scale that is almost impossible to comprehend. To give you a sense of perspective, consider this. The escape velocity from the surface of Earth is about 11 kilometers per second. That means a rocket needs to travel at least that fast to break free from Earth's gravity. The escape velocity from the surface of the Sun is much higher, around 617 kilometers per second. But the escape velocity from the event horizon of a black hole? It equals the speed of light, which is approximately 300,000 kilometers per second. That number is so large it is almost meaningless to our everyday experience. And yet, that is the reality of what a black hole represents. To understand how this extreme gravity comes to exist, we need to talk about the concept of spacetime. Albert Einstein revolutionized our understanding of gravity with his general theory of relativity, published in 1915. Before Einstein, scientists thought of gravity the way Isaac Newton did, as a force that acted between masses across empty space. Einstein showed us something far more profound. He revealed that space and time are not separate things. They are woven together into a single fabric called spacetime. And massive objects do not simply pull other objects toward them. They actually warp and curve the fabric of spacetime around them. The more massive an object, the more it curves spacetime. Imagine placing a bowling ball on a stretched rubber sheet. The sheet sags and curves around the ball. Now place a marble on that sheet near the bowling ball, and the marble rolls toward the heavier object, not because some invisible force is pulling it, but because the geometry of the surface itself has changed. A black hole takes this concept to its absolute extreme. Its mass is so concentrated that it punches an infinitely deep well into spacetime, creating a gravitational pull so extreme that not even light, traveling at the fastest speed anything in the universe can achieve, can climb back out. But where do black holes actually come from? How does something this extreme form in the first place? The most common and well-understood origin story of a black hole begins with a star, but not just any star. We are talking about a star that is at least about 20 to 25 times more massive than our own Sun, though some estimates vary depending on conditions. Throughout most of its life, a massive star exists in a state of balance. Its core is an enormous nuclear furnace, fusing hydrogen atoms into helium, and releasing enormous amounts of energy in the process. That energy pushes outward against gravity, which is constantly trying to crush the star inward. For millions of years, these two forces, the outward push of nuclear fusion and the inward pull of gravity, remain in perfect balance. The star shines brilliantly, but stars do not burn forever. Eventually, after millions of years of nuclear burning, the star exhausts its fuel. The nuclear furnace in its core begins to shut down. And when that happens, the outward pressure that was holding gravity at bay suddenly disappears. Gravity wins. In a fraction of a second, the core of the star collapses catastrophically inward. This collapse happens so rapidly and releases such an enormous burst of energy that the outer layers of the star are blasted away in a colossal explosion called a supernova, one of the most energetic events in the known universe. The explosion can briefly outshine an entire galaxy containing hundreds of billions of stars. But what remains at the center after the explosion? That depends on how massive the original star was. If the core that remains is between roughly 1.5 and 3 solar masses, it becomes an incredibly dense object called a neutron star. But if the remaining core is more massive than that, gravity continues its collapse without anything stopping it. The core is crushed down further and further, past the density of a neutron star, into a point of essentially zero volume and infinite density. That point is called a singularity, and wrapped around it by the warped fabric of spacetime is the event horizon. A black hole is born. This is the most common type of black hole in the universe, known as a stellar mass black hole. These typically contain anywhere from a few times to perhaps 100 times the mass of our Sun, compressed into a region of space smaller than a city. But as extraordinary as stellar mass black holes are, they are just one variety of these cosmic monsters. The universe contains black holes that range from the relatively modest stellar variety to something almost incomprehensibly larger, objects called supermassive black holes that lurk at the centers of most large galaxies, including our own Milky Way, containing millions and even billions of times the mass of the Sun. The story of black holes is not just a story about destruction and darkness. It is a story about the fundamental architecture of the cosmos, about how matter, energy, space, and time are connected in ways that continue to challenge and inspire the greatest scientific minds on Earth. And we are only just beginning, because understanding what a black hole is merely the first step. The real questions: how did the first black holes form, what happens when you fall into one, and what secrets do they hold about the nature of reality itself, those answers lie just ahead. Every black hole has a story, and that story almost always begins with a star. Not just any star, but one of the most extreme objects the universe is capable of producing. To understand how a black hole is born, we first need to understand how stars live, because it is in the final moments of a stellar life that the universe performs one of its most spectacular and violent acts. Stars are, at their heart, a perpetual battle between two opposing forces. Gravity, the inward crush of a star's own enormous mass, is constantly trying to collapse the star in on itself. Pushing back against that gravitational squeeze is the energy produced by nuclear fusion happening in the star's core. Deep inside a star like our Sun, hydrogen atoms are being fused together under unimaginable pressure and temperature to form helium, releasing tremendous amounts of energy in the process. This outward radiation pressure is what keeps a star puffed up and shining. For billions of years, these two forces maintain a delicate, almost miraculous balance called hydrostatic equilibrium. But not all stars are created equal. The most critical factor in determining a star's fate is its mass. Our Sun, a relatively modest star by cosmic standards, will one day exhaust its hydrogen fuel and swell into a red giant before shedding its outer layers and leaving behind a dense stellar remnant called a white dwarf. It will not become a black hole. But for stars that are significantly more massive, stars containing at least 20 to 25 times the mass of our Sun, the ending is far more dramatic. These stellar giants, known as massive stars or supergiants, burn their fuel so ferociously that they live comparatively short lives. While our Sun will shine for roughly 10 billion years, a star 20 times more massive might only last 10 million years, blazing brilliant and hot before racing toward a cataclysmic end. As a massive star ages, it does not simply run out of hydrogen and stop. Instead, it undergoes a series of increasingly intense fusion stages. When the hydrogen in the core is exhausted, gravity compresses the core further, raising temperatures to the point where helium can begin to fuse into carbon. When the helium runs out, carbon ignites. Then neon, then oxygen, then silicon. Each successive stage of fusion produces heavier elements, and each stage burns faster than the last. What took millions of years for hydrogen takes thousands of years for helium, hundreds for carbon, and mere days for silicon. The star's interior develops a layered onion-like structure, with shells of different elements fusing at different depths, all surrounding an increasingly dense iron core at the center. And here is where the physics becomes truly extraordinary. Iron is the universe's cosmic dead end when it comes to fusion. Fusing elements lighter than iron releases energy. But fusing iron actually consumes energy rather than releasing it. When a massive star's core fills up with iron, nuclear fusion can no longer produce the outward pressure needed to resist gravity. The iron core is, in a very real sense, a ticking time bomb. It accumulates mass rapidly as silicon in the surrounding shell continues to burn and deposit more iron into the core. There is a critical threshold, a limit discovered by the physicist Subrahmanyan Chandrasekhar, beyond which electron degeneracy pressure, the quantum mechanical force that keeps matter from collapsing further, cannot hold the core up. That limit is roughly 1.5 times the mass of our Sun. When the iron core exceeds this limit, the end comes with terrifying swiftness. In less than a single second, a core that was roughly the size of Earth collapses down to a sphere only about 20 kilometers across. 20 kilometers. In the span of time it takes to blink your eye, a volume of matter containing more mass than the entire Sun is compressed into something the size of a small city. The collapse happens so fast and so violently that the infalling outer layers of the star actually bounce off the newly formed dense core. This rebound sends a shockwave blasting outward through the star, and what follows is one of the most energetic events in the known universe. A supernova. The outer layers of the star are expelled at a significant fraction of the speed of light, radiating as much energy in a matter of seconds as our Sun will release over its entire 10 billion year lifetime. For a brief period, a single exploding star can outshine an entire galaxy containing hundreds of billions of stars. These titanic explosions seed the cosmos with heavy elements, the very iron in your blood, the calcium in your bones, the gold in your jewelry, all forged in the hearts of dying stars and scattered across space by supernova explosions. In this sense, every living thing on Earth is quite literally made of stardust. But what is left behind after the explosion? That depends entirely on the mass of the remnant core. If the surviving core contains between roughly 1.5 and about 3 times the mass of the Sun, the result is a neutron star. A neutron star is already among the most extreme objects in the universe, a sphere of densely packed neutrons only about 20 kilometers across, spinning hundreds of times per second, with a magnetic field trillions of times stronger than Earth's. However, if the remnant core is more massive than about 3 solar masses, neutron degeneracy pressure, the last line of quantum mechanical defense against gravitational collapse, is itself overwhelmed. And at that moment, nothing in the known laws of physics can stop the collapse from continuing. The core does not stop at neutron star density. It keeps collapsing, and collapsing, until it reaches what we believe to be a singularity, a point of infinite density where the curvature of spacetime itself becomes infinite and the known laws of physics break down entirely. A stellar black hole is born. This type of black hole, born from the collapse of a massive star, is called a stellar mass black hole. They typically contain between a few and a few tens of solar masses. They are the most common type of black hole we know of, and our galaxy alone is estimated to contain anywhere from 10 million to 1 billion of them, scattered throughout the stellar population of the Milky Way like invisible seeds of collapsed spacetime. But stellar collapse is not the only pathway to a black hole's creation. As our understanding of the cosmos has deepened, scientists have come to suspect that some black holes form through entirely different and far more mysterious processes that trace back not to dying stars but to the chaotic, violent conditions of the very early universe itself. And some black holes are so unimaginably massive, millions or even billions of times the mass of our Sun, that stellar collapse alone cannot account for their existence. Understanding how those giants came to be requires us to look even deeper into the universe's past. Before we can explore where these cosmic giants come from, we need to understand exactly what a black hole is, not just in the loose popular sense, but in the precise, almost philosophically staggering sense that physics demands. Because a black hole is not simply a hole in space. It is not a vacuum cleaner floating in the cosmos, sucking up everything around it. It is something far stranger, far more elegant, and far more terrifying than that. It is a region of spacetime where gravity has become so overwhelmingly powerful that the very fabric of reality, space, and time themselves are bent beyond any possibility of return. To truly grasp this, we need to take a journey inward, layer by layer, into the anatomy of one of the universe's most extreme objects. Imagine you are an astronaut, drifting in a spacecraft somewhere near a stellar mass black hole. At a great distance, you feel its gravity, but it is no different from the gravity you would feel near any massive object. If our Sun were somehow replaced by a black hole of identical mass, Earth would simply continue orbiting as it always has. Nothing dramatic. Nothing catastrophic. Gravity at a distance is gravity. But as you pilot your spacecraft closer and closer to this black hole, something begins to change. The gravitational pull grows stronger with every kilometer you shed, and at a certain precise boundary, something fundamental shifts. You have reached the event horizon. The event horizon is perhaps the most iconic concept in all of black hole physics, and it is also one of the most misunderstood. Many people imagine it as a physical surface, like a wall or a membrane, something you could crash into. But the event horizon is not a surface at all. It has no material existence. If you were falling toward a black hole in free fall, the event horizon would be invisible and undetectable to you as you crossed it. You would feel no jolt, no collision, no dramatic sensation. If the black hole were massive enough, the gravitational tidal forces at the event horizon might be gentle enough that you would not even realize you had crossed over. And yet, crossing it would seal your fate absolutely and irrevocably. What the event horizon represents is a mathematical boundary in spacetime, specifically the boundary beyond which the escape velocity exceeds the speed of light. Escape velocity is the speed required to break free from a gravitational field. On Earth, it is about 11 kilometers per second. On the surface of our Sun, it is much higher. But at the event horizon of a black hole, escape velocity reaches exactly the speed of light, 300,000 kilometers per second. And since nothing in the universe, not matter, not information, not even light itself, can travel faster than that, nothing that crosses the event horizon can ever escape. The universe on the outside becomes permanently inaccessible. You are inside, and inside is all there will ever be. The size of the event horizon, what physicists call the Schwarzschild radius, depends entirely on the mass of the black hole. For a black hole with the mass of our Sun, the Schwarzschild radius would be about 3 kilometers. That entire solar mass, compressed into a sphere just 6 kilometers across. For a supermassive black hole billions of times more massive, the event horizon could be larger than our entire solar system. The concept was first worked out mathematically by Carl Schwarzschild in 1916, just months after Albert Einstein published his general theory of relativity, and remarkably, Schwarzschild derived his solution while serving on the front lines of the First World War. He died shortly afterward, never seeing the full implications of his discovery unfold. Now here is where things grow truly strange. We have described the event horizon as a boundary of no return, but what lies beyond it? What happens as you continue falling inward, past that invisible threshold, deeper and deeper into the black hole? General relativity gives us a clear mathematical answer, but that answer leads to a place where physics as we understand it completely breaks down. That place is the singularity. In the context of a non-rotating black hole, the singularity is described as a single point at the center, a point of infinite density and infinitely curved spacetime. All the mass of the black hole is concentrated here, crushed into a region of zero volume. Mathematically speaking, the density becomes infinite, and all the equations of physics choke and fail. This is what physicists call a breakdown of the theory. General relativity, our best description of gravity, simply cannot tell us what is happening at the singularity. The numbers it produces are not just large, they are meaningless. Infinity is not a physical quantity. It is a signpost telling us that our theory has reached the edge of its own validity. Most physicists believe that what the singularity really signals is our ignorance. It tells us that to understand what actually happens at the center of a black hole, we need a theory that combines general relativity with quantum mechanics, a theory of quantum gravity that we do not yet possess. String theory, loop quantum gravity, and other emerging frameworks attempt to address this, but none has yet produced a complete, experimentally verified picture. The singularity remains one of the most profound open questions in all of theoretical physics. But not all black holes are the same in their structure. So far we have been discussing what is called a Schwarzschild black hole, a perfectly spherical, non-rotating black hole. In reality, most black holes are expected to rotate, because the stars that form them were themselves rotating, and angular momentum is conserved through the collapse. A rotating black hole, described by what is called the Kerr metric, has a more complex anatomy. It possesses not one but two key boundaries. There is still the outer event horizon, the point of no return. But inside that is another structure called the inner Cauchy horizon. Between them lies a region called the ergosphere. The ergosphere is one of the most fascinating structures in all of astrophysics. It surrounds the outer event horizon but extends beyond it, particularly around the equatorial region of the rotating black hole. Inside the ergosphere, something extraordinary happens. Spacetime itself is being dragged around by the rotation of the black hole, a phenomenon known as frame dragging. Within the ergosphere, it becomes physically impossible for any object to remain stationary relative to the distant stars. Space itself is moving, and it is moving faster than any engine could counteract. You are dragged along whether you like it or not. However, unlike crossing the event horizon, being inside the ergosphere does not doom you. You can still escape, provided you move in the right direction. And this leads to one of the most elegant theoretical phenomena in all of physics, a process called the Penrose process, through which energy can theoretically be extracted from a rotating black hole by an object that enters the ergosphere and cleverly splits apart. Roger Penrose proposed this mechanism in 1969, and it has profound implications. It means that black holes are not simply passive absorbers of energy. A rotating black hole carries an enormous reservoir of rotational energy locked in the spin of spacetime around it, and under the right conditions, that energy can be unleashed. Some scientists believe that similar mechanisms, involving magnetic fields and plasma rather than splitting particles, may be responsible for the tremendous jets of energy that we observe blasting out of active black holes across the universe. And then there is the question of what it actually feels like to cross the event horizon. Beyond the mathematics, let us sit with this moment as a thought experiment. You are falling feet first toward the event horizon of a stellar mass black hole. As you approach, you would begin to experience what physicists call tidal forces, the difference in gravitational pull between your feet, which are closer to the singularity, and your head. This difference would grow rapidly. The gravity at your feet would be dramatically stronger than at your head, and your body would be stretched vertically while simultaneously compressed horizontally. Physicists have a wonderfully expressive term for this process. They call it spaghettification. You would be stretched into a long, thin strand of matter, like cosmic spaghetti, long before you ever reach the event horizon of a small black hole. However, near a supermassive black hole with an event horizon billions of kilometers across, the tidal forces at the event horizon itself would be gentle enough that you could cross over in one piece. You would feel nothing remarkable as you pass through, and yet your future would be absolutely determined. Every possible path your spacecraft could take, every direction you could point your thrusters, every trajectory available to you, would lead to the singularity. Time and space switch roles inside the event horizon in a deeply precise mathematical sense. In normal spacetime, you can choose freely which direction in space to move, but you cannot avoid moving forward in time. Inside the event horizon, the singularity becomes your future the way tomorrow is your future. It is not a place in space you are falling toward. It is a moment in time you cannot avoid. This realization, that the singularity is temporal rather than merely spatial, is one of the most mind-bending conclusions of general relativity. And it is the reason why no rocket, no engine, and no force in the universe can save you once you have crossed over. You cannot thrust away from your own future any more than you can thrust away from tomorrow. The event horizon is the universe's most absolute and unbreakable boundary, drawn not in space but in the very nature of time itself. Understanding this anatomy, the event horizon as a threshold of no return, the singularity as the breakdown of known physics, the ergosphere as a spinning reservoir of extractable energy, gives us the framework we need to ask an even deeper question. How do black holes interact with the universe around them? How do they grow, feed, and sometimes spectacularly announce their presence across billions of light-years of space? Because while a black hole may trap everything that falls inside it, the region just outside is anything but quiet. Not all black holes are created equal. The universe, in its extraordinary creativity, has manufactured these gravitational monsters in at least 3 distinct ways, each producing a different breed of black hole with different masses, different origins, and different roles in the cosmic story. To understand black holes fully, you need to understand that the term itself is really an umbrella, sheltering objects that range from a few times the mass of our Sun all the way up to tens of billions of solar masses. The difference between the smallest and largest is so vast it almost defies comprehension, like comparing a grain of sand to a mountain range. And yet every single one of them operates by the same ruthless principle, gravity so extreme that nothing, absolutely nothing, can escape. Let us begin with the most well-understood variety, the stellar black hole. These are the original black holes of scientific imagination, the ones born from the violent deaths of massive stars. When a star with a mass roughly 20 or more times that of our Sun burns through its nuclear fuel, something extraordinary and catastrophic happens. For millions of years, the star has maintained a delicate balance. The outward pressure of nuclear fusion pushing against the inward crush of gravity. But fusion cannot last forever. When the star finally exhausts its fuel, that outward pressure vanishes in an instant, and gravity wins without contest. The core collapses in less than a second, so fast and so violently that the outer layers of the star rebound outward in a catastrophic explosion we call a supernova. What remains at the center after that explosion depends entirely on the mass of the original star. Stars of moderate mass leave behind a neutron star, an object so dense that a teaspoon of its material would weigh 1 billion tons. But for the most massive stars, even a neutron star cannot hold itself together against such overwhelming gravity. The remnant core continues collapsing, punching through even the resistance of densely packed neutrons, until it vanishes behind an event horizon. A stellar black hole is born. These objects typically range from about 3 to roughly 100 solar masses, and they are scattered throughout our galaxy by the billions. The Milky Way alone is estimated to contain somewhere between 10 million and 1 billion stellar black holes, most of them invisible, detected only when they betray their presence through their gravitational influence on nearby stars or by pulling material from a companion star and heating it to X-ray emitting temperatures. One of the most famous examples of a stellar black hole caught in action is Cygnus X1, located about 6,000 light-years from Earth. Discovered in the early 1970s as one of the brightest X-ray sources in the sky, Cygnus X1 is a binary system where a black hole of approximately 21 solar masses is actively feeding from a massive companion star. The material stripped from that star spirals inward and heats to millions of degrees, releasing a torrent of X-rays that astronomers have been studying for decades. Cygnus X1 was actually at the center of a famous scientific wager. Stephen Hawking bet against the idea that it harbored a black hole. He eventually conceded the bet, acknowledging the evidence had become overwhelming. But stellar black holes, as massive as they sound, are essentially the lightweight division compared to what lurks at the hearts of galaxies. Supermassive black holes represent a category so extreme that our intuitions about physics and scale completely break down. These are the true titans of the universe, objects with masses ranging from 1 million to tens of billions of solar masses. Every large galaxy that astronomers have examined closely appears to harbor one of these behemoths at its center. Our own Milky Way is no exception. At the very heart of our galaxy, roughly 26,000 light-years from Earth, sits a supermassive black hole called Sagittarius A star. It weighs in at approximately 4 million solar masses and sits at the gravitational nucleus around which our entire galaxy slowly rotates. The evidence for Sagittarius A star accumulated over decades through painstaking observations. Astronomers, particularly teams led by Andrea Gerzert-Uckler and Reinhard Genzel in Germany, tracked the motions of stars in the galactic center for over 20 years, watching them complete full orbits around something invisible. The speeds of these stars were extraordinary, some traveling at several percent the speed of light in tight orbits that could only be explained by an enormous concentration of mass packed into a tiny space. In 2020, Gez and Genzel shared the Nobel Prize in Physics for this work, cementing our understanding that supermassive black holes are real, present, and central to galaxy formation itself. Then in April 2022, the Event Horizon Telescope collaboration released the first direct image of Sagittarius A star, a glowing ring of hot gas surrounding a dark central shadow, the actual silhouette of a 4 million solar mass black hole 44 million kilometers across. But even Sagittarius A star is modest by supermassive standards. The black hole at the center of galaxy M87, the first black hole ever directly imaged back in 2019, clocks in at 6.5 billion solar masses. Its event horizon is so large that our entire solar system would fit comfortably within it. If you place that black hole where our Sun is, it would swallow Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, and extend far beyond. Understanding how these giants grew to such impossible sizes is one of the great open questions in astrophysics. They must have grown through a combination of consuming enormous amounts of gas and dust and merging with other black holes over cosmic timescales. But the details remain a subject of active and vigorous debate. And then there is the third and most mysterious category, one that stretches scientific imagination to its absolute limits: primordial black holes. These hypothetical objects would not have formed from dying stars or galactic processes at all. Instead, they may have formed in the first fraction of a second after the Big Bang itself, when the universe was so dense and so hot that random fluctuations in the distribution of matter could have compressed regions of space directly into black holes, without any star ever needing to live and die first. Primordial black holes are theorized to span an enormous range of masses, potentially from as small as the Planck mass, which is unimaginably tiny, all the way up to thousands of solar masses or more, depending on when exactly during the Big Bang they formed. The reason primordial black holes attract such intense scientific interest is not just their exotic origin. It is what they might explain. One of the deepest mysteries in cosmology is the nature of dark matter, the invisible substance that makes up roughly 27% of the total energy content of the universe. We know it exists because we can observe its gravitational effects on galaxies and galaxy clusters. But we have never directly detected a single dark matter particle despite decades of searching. Some physicists have proposed that primordial black holes, if they were formed in large numbers early in the universe's history, could account for some or all of the dark matter. A universe quietly threaded with ancient black holes, invisible and undetectable except by gravity, would look exactly like the dark matter we observe. So far, the evidence is tantalizing but inconclusive, with certain mass ranges for primordial black holes ruled out by observation but others remaining wide open. These three categories, stellar, supermassive, and primordial, paint a picture of a universe far more populated with black holes than most people ever imagine. They are not rare curiosities or distant dangers. They are fundamental features of the cosmic landscape, woven into the structure and evolution of everything we see. And this raises a question that scientists are only beginning to answer. What role do these objects play not just as endpoints of stars or relics of the Big Bang, but as active, dynamic engines that shape the galaxies and large-scale structures around them? Because black holes, it turns out, do not simply sit passively in the darkness consuming what falls their way. They feed, and when they feed intensely enough, they give rise to some of the most luminous and energetic phenomena in the entire observable universe. To truly understand what a black hole is, you cannot rely on everyday intuition. The physics that governs these extraordinary objects operates at a level so far removed from ordinary human experience that even the language we use begins to strain under the weight of what it must describe. And yet the mathematics is precise, elegant, and in many ways, beautiful. To grasp a black hole, you must first grasp the two great pillars of modern physics that made their prediction possible: gravity and the theory of general relativity. For centuries, gravity was understood through the lens of Isaac Newton. His law of universal gravitation, formulated in the 17th century, described gravity as a force, an invisible pull between any two masses across empty space. It was extraordinarily successful. It predicted the motions of planets, explained the tides, and allowed engineers to calculate the trajectories of cannonballs and, eventually, spacecraft. But Newton himself admitted something troubling. He could describe how gravity behaved, but he had absolutely no idea what it actually was. How could one object pull on another across the vast emptiness of space without any physical connection between them? He called it action at a distance and left the mystery unsolved. The answer came more than 2 centuries later, in 1915, when Albert Einstein published his general theory of relativity. What Einstein revealed was nothing short of a revolution in our conception of reality. Gravity, he showed, is not a force at all in the traditional sense. It is a consequence of the curvature of space-time. This is the key insight that unlocks everything about black holes, so it is worth spending time understanding it properly. Einstein unified space and time into a single four-dimensional fabric called space-time. Every object with mass or energy warps this fabric around it, bending and curving it the way a heavy ball resting on a stretched rubber sheet creates a depression. Other objects moving through this curved space-time follow the curves rather than straight lines, and this is what we experience as gravity. The Earth orbits the Sun not because the Sun is pulling it with some mysterious force, but because the Sun's enormous mass has curved the spacetime around it, and the Earth is simply following the most natural path available through that curved geometry. This has a profound implication that Newton never could have anticipated. Because spacetime itself is curved, not just the paths of massive objects but even light must follow these curves. Light always travels in what physicists call a geodesic, the straightest possible path through spacetime. But if spacetime is curved, even that straightest path becomes bent. This was confirmed in spectacular fashion during the solar eclipse of 1919, when astronomers measured starlight bending around the Sun by exactly the amount Einstein's equations predicted. The world recognized instantly that something fundamental had changed in our understanding of the universe. Now consider what happens when you take this concept of curved spacetime and push it to an extreme. Imagine compressing a mass so completely, so totally, that the curvature it creates becomes infinite. At some critical point, the warping of spacetime becomes so severe that not even light, traveling at approximately 300,000 kilometers per second, the fastest anything can move in the universe, can follow a path that leads back outward. It simply cannot escape. The geometry of spacetime itself has closed off all possible escape routes. This is the event horizon, and the region inside it is what we call a black hole. The mathematics that describes this scenario comes directly from Einstein's field equations, the set of 10 interrelated differential equations that form the core of general relativity. These equations relate the curvature of spacetime to the distribution of mass and energy within it. They are notoriously difficult to solve. In fact, in the months immediately following Einstein's publication of general relativity, a German physicist and astronomer named Karl Schwarzschild found the first exact solution while serving on the Russian front during the First World War. Schwarzschild solved Einstein's equations for the simplest possible case, a perfectly spherical, non-rotating mass. The solution revealed something extraordinary. At a specific radius around any sufficiently compressed mass, the equations broke down in a way that signaled a point of no return. That radius is now called the Schwarzschild radius, and the boundary it defines is the event horizon of a non-rotating black hole. The Schwarzschild radius depends entirely on mass. For the Sun, it would be roughly 3 kilometers. The entire mass of our star, compressed into a sphere just 3 kilometers across, would form a black hole. For the Earth, the Schwarzschild radius is even smaller, just under 9 millimeters, about the size of a marble. Of course, neither the Sun nor the Earth will ever actually be compressed to these scales. The potential for this kind of extreme curvature is baked into the fabric of reality for any mass, large or small. One of the most mind-bending consequences of general relativity near a black hole is what happens to time itself. Einstein showed that gravity not only curves space but also dilates time. The stronger the gravitational field, the more slowly time passes relative to a distant observer. Near the event horizon of a black hole, this effect becomes extreme. An astronaut falling toward a black hole would, from their own perspective, experience time passing normally. They would feel, at least for a while, nothing unusual as they crossed the event horizon. But to a distant observer watching this astronaut through a hypothetical telescope, something strange would appear to happen. As the astronaut approached the event horizon, they would appear to slow down, their image becoming redder and dimmer, stretched across time as light from their position struggled to climb out of the deepening gravitational well. They would never quite appear to cross the horizon. They would seem to freeze, gradually fading away across eternity. Two observers, the same event, two completely different realities. This is not a paradox or an illusion. It is exactly what the physics of general relativity predicts. This phenomenon is known as gravitational time dilation, and has been measured and confirmed here on Earth, albeit in tiny amounts, using extraordinarily precise atomic clocks placed at different altitudes. Clocks at higher altitudes, where gravity is slightly weaker, run fractionally faster than clocks at sea level. The effect is small but real and measurable, and it is the same physics amplified to its ultimate extreme near a black hole. At the very center of a black hole, inside the event horizon, general relativity predicts something that physicists still wrestle with today, the singularity. This is a point, or in the case of rotating black holes, a ring, where density becomes infinite, where the curvature of spacetime becomes infinite, and where the equations of general relativity simply stop making sense. Most physicists believe the singularity is not a real physical feature of the universe, but rather a signal that general relativity, despite its astonishing accuracy, breaks down at these extremes. To understand what truly happens at the center of a black hole, we will likely need a complete theory of quantum gravity, something that remains one of the most urgent and elusive goals in all of theoretical physics. Understanding the physics of black holes means standing precisely at the border where our best theories begin to fail us, where the universe reveals that it has secrets we have not yet found the right language to describe. And this tension, between what we know and what remains just beyond our grasp, is exactly what makes black holes one of the most fertile and exciting frontiers in all of science. Because as dramatic as the physics of the event horizon and the singularity are, the story of what black holes actually do in the universe, how they radiate, how they interact, and how they might ultimately decay, reaches even deeper into the unknown. Imagine, for a moment, that you are an astronaut. Not just any astronaut, but one with the extraordinary misfortune, or perhaps the extraordinary curiosity, to find yourself falling directly toward a black hole. What would you experience? What would you see, feel, and ultimately become? This is not merely a thought experiment for philosophers. It is a question that physicists have wrestled with in precise mathematical detail, and the answers are among the most mind-bending, counterintuitive, and genuinely terrifying conclusions that science has ever produced. Let us begin far from the black hole, at a safe distance where gravity is still manageable. From here, the black hole appears as a dark sphere surrounded by a glowing halo of warped light. Stars behind it are bent into rings and arcs. The closer you drift, the more dramatically the light around you distorts. You are not yet in danger, but you are beginning to enter a region where spacetime itself is measurably curved. Your instruments would detect a growing tidal force, the difference in gravitational pull between the parts of your body closer to the black hole and those farther away. Near a stellar mass black hole, this tidal difference would become catastrophically significant well before you reach the event horizon. Near a supermassive black hole, the tidal forces at the event horizon are actually far gentler, because the horizon is so much farther from the singularity. This distinction matters enormously for what happens next. The process physicists call spaghettification is one of those rare scientific terms that perfectly describes exactly what it means. As you approach a black hole closely enough, the difference in gravitational pull along the direction of your fall becomes so extreme that your body is stretched vertically and simultaneously squeezed from the sides. The end nearest the black hole is pulled more strongly than your midsection, and your midsection more than your feet if you are falling head first. This stretching and compressing transforms anything with physical extent, whether it is a star, a spacecraft, or a human being, into a long, thin strand of matter. Like cosmic taffy being pulled apart, atom by atom, molecule by molecule, the structural integrity of any object cannot resist these tidal forces once they exceed a critical threshold. You would be drawn out into a thin stream of particles spiraling down toward the singularity. Now here is where the story becomes genuinely strange, because the experience of spaghettification depends entirely on whose perspective we adopt. And in general relativity, perspective is everything. If you are a distant observer watching someone fall into a stellar mass black hole, you would never actually see them cross the event horizon. As the infalling person gets closer, the light they emit takes longer and longer to climb back out against the intense gravitational well. Their image appears to slow down, becoming dimmer, redder, and more frozen as light becomes increasingly redshifted. To you, the outside observer, they appear to hover just outside the event horizon forever, gradually fading away into a ghostly reddened smear. Time itself, from your perspective, appears to slow to a halt for the infalling person. This is gravitational time dilation taken to its ultimate extreme. But now adopt the perspective of the person actually falling. They would notice something astonishing. They would cross the event horizon without any dramatic fanfare, at least not immediately in the case of a supermassive black hole. There is no physical wall there, no visible boundary, no sign marking the point of no return. Spacetime at the event horizon of a large enough black hole is not dramatically curved in a locally perceptible way. An astronaut falling freely into a supermassive black hole the size of the one at the center of our galaxy could cross the event horizon and not immediately realize it. They might look around and see the universe behind them, though it would begin to appear increasingly compressed and blue-shifted into a bright ring. They would have time to think, to observe, to record data. But they would have no way to communicate any of it to the universe they left behind. Every signal they sent would require faster-than-light travel to escape, and that is precisely what the event horizon prevents. As they continue inward, even past the event horizon of a supermassive black hole, eventually the tidal forces grow. Eventually spaghettification does claim them. The singularity at the center is not just a place in space but a moment in time, a future from which there is no detour. Every path through spacetime inside the event horizon leads inevitably to the singularity. Trying to avoid it is as physically meaningful as trying to avoid tomorrow. You cannot turn around and fly away from next Tuesday, and inside a black hole, you cannot turn around and fly away from the singularity. It is simply where all futures inside the horizon lead. This concept of the light cone is crucial to understanding why escape is impossible. In flat spacetime, a light cone represents all the possible directions a signal or an object can travel into the future. Outside a black hole, some of these directions point away from the center. At the event horizon, the light cone tilts so severely that even the outward edge is pointing directly sideways, toward the horizon but no longer away from it. Inside the event horizon, the light cone tilts entirely inward. Every direction that the future can take, every possible trajectory, every possible choice, curves toward the singularity. This is not a prison with walls you might break through. It is a geometry from which there is no logical exit. But what about the information carried by the infalling astronaut? Their memories, the atomic structure of their body, the quantum states of every particle that once constituted them? This is where we arrive at one of the most profound and fiercely debated problems in all of theoretical physics, one that cuts right to the heart of how we understand reality at its deepest level. It is called the black hole information paradox, and it has occupied some of the greatest minds in physics for half a century without a fully satisfying resolution. The question is not just academic. If information can truly be destroyed when it falls into a black hole, then one of the most fundamental principles of quantum mechanics, that information is always preserved somewhere in the universe, is violated. And if that principle falls, the very foundation on which our understanding of particles, forces, and the structure of reality rests begins to crack. Stephen Hawking first formulated this paradox seriously in the 1970s when he discovered that black holes actually emit radiation and can eventually evaporate entirely. If a black hole can radiate away all of its mass and eventually disappear, and if that radiation carries no imprint of what fell in, then everything that ever entered, every book, every star, every astronaut, every quantum of information, simply ceases to exist anywhere in the universe. And quantum mechanics says that is categorically impossible. Something must give. Either Hawking radiation secretly encodes the information somehow, in a way we do not yet understand, or the black hole does not fully evaporate, or quantum mechanics itself needs modification. None of these options is comfortable, and none has been definitively proven. The sheer drama of what happens when matter crosses the event horizon, the spaghettification, the tilting of time, the inevitable descent toward a singularity, and the fundamental philosophical crisis of whether information survives at all, makes the interior of a black hole the most extreme environment we can conceive of. It is a region where our most carefully constructed theories are pushed beyond their limits, and where the universe seems to be insisting that we are still missing something fundamental. And understanding what that something is, piecing together what really happens in those final moments before the singularity, requires us to grapple directly with the extraordinary phenomenon that Hawking placed at the center of this debate, the remarkable and deeply mysterious fact that black holes, despite everything, are not entirely black.